been asked to give a workshop on speleothem age modeling. And well, to admit, I thought a lot about how to do that with almost 100 people. And I have a lot of experience now gained a lot of experience now in the last 2 years with online teaching. And my experience is that you can do these things with small groups, let's say of 10 to 15 people. It's very difficult to do things like that with groups of 30 people, and it's impossible to do it like that with 100 people. So I decided to give you kind of a lecture, but also to upload the code. So you should be able to do everything that I don't do on your own screen. And then I can just ask you to interrupt me and ask questions whenever necessary. At the beginning, I want to show, give you a short introduction about speleothem age models, what's behind that, all of that. Why do we need these age models? What has been done in the past, and so on. And then I will quickly move on to give you a brief introduction. What is R? Why do I use R? Give you a very, very, very brief introduction into the basic syntax and the applications. And then I will show, then I will start with the workshop. I will show you some basic age modeling. I will start with linear interpolation, briefly show you some splines, show you how to plot the proxy records once you have an age model, and then I will show you how to apply StalAge with R. And if there's enough time in the end, I will also show you how to apply Bchron. So I think it's that should be a nice start, so to say, with age modeling. And in the end, hopefully, everybody of you should be able to at least create a linear interpolation age model, and I would be very happy if that would be the case. Okay, I'd like to start with a short motivation why age modeling is important. And actually, Martin Blau made a literature review in 2010, so almost 12 years ago now. And there he reviewed 93 papers published in 2008 in Quaternary Geochronology, Quaternary Science Reviews, the Journal of Quaternary Science, and the Holocene. And he found that 60 of these papers did not tell which point estimates were used. Well, this is particularly important if you do 14C dating, but it's also important for uranium series dating, in particular if you have very old ages. 71 of these 93 papers didn't mention the software that was used. 65, and that's really, really fascinating, of these 93 papers didn't indicate whether age depth uncertainties were calculated. So they didn't provide an uncertainty for their age models. And 18 did not specify how they calculated the age depth model, right? So this shows that although we use all these kinds of expensive and state-of-the-art techniques, we spend a lot of time and money on dating, and then we do something really strange to calculate the age model, and we don't care about the uncertainties arising from the construction of the age model. So this is really, it's really bad actually, and we could do much better. So this is 10 years ago, but I think it has improved in the last decade, but I think there's still a lot of room for improvements. What Martin found out at that time was that 31 of these 93 papers used linear interpolation, 18 did some kind of regression or polynomial regression, and 11 used some kind of Bayesian age depth modeling. Okay, so just a few words about why we need speleothem age models. Well, you all know what we do when we want to reconstruct the climate of the past is we measure any kind of proxy, usually at a very high resolution. So here you see stalagmite ER76 from Grotta di Ernesto. It's a stalagmite which is almost, I think, 20 centimeters long or so. And here you can see the carbon isotope profile. And here you can see the oxygen isotope profile, and you can see that it's 35 centimeters long, actually. So, and we measured here the carbon isotopes and the oxygen isotopes at very high resolution. I think here with 200 microns or something like that. So we have a high resolution proxy profile, right? And then we also do some dating also against the distance from top. And here you can see we have 1, 2, 3, 4, 5, 6, 7, let's say 10 or 12 thorium uranium ages. So this has been done, I think in 2009 or so, and we have 11 TIMS thorium uranium ages. And you all know that meanwhile, it's possible to do that a little bit faster. So usually we have more ages, so we have a higher resolution of the ages, but still, right, the resolution of the proxies is usually in the range of micrometers to millimeters, and the resolution of the ages is in the range of millimeters to centimeters. So the resolution of the proxy is usually much, much higher than the resolution of the ages. And that means that we need to determine the age in between two adjacent ages, right? So here we have an age of 4.5, here we have an age of 4,000 years, right? And in between, we don't know if the age model did something like that or something like that, or maybe there was a hiatus, we don't know, right? But we need to know this if we want to plot the proxy against age. Right, so that's the basic question. So we have a proxy profile against distance from top, a high resolution proxy profile. We also have the ages against distance from top. Usually we have the ages at lower resolution, and we want to combine that. And in the end, we want to plot the proxy against age. Right, so that's what we want to do. And ideally, to plot the proxy data versus age, we would need a relationship between age and distance, and ideally that would be a mathematical function, right? So we need a fit of the age data. The problem now is that the growth rate of speleothems, and therefore distance from top, depends on a complex interplay of various parameters, right? Such as drip rate, supersaturation with respect to calcite, which in turn depends on PCO2 in the soil and the cave, temperature, film thickness, splashing effects, and so on. So there are many, many parameters which influence the growth rate of speleothems, right? And even if we have growth models for speleothems, so maybe know some of these papers where people try to model the growth rate in the dependence of temperature and drip rate and so on, the relationship is very complex, and that's even more difficult. We don't know the evolution of the parameters in the past, right? We don't know the drip rate in the past, the temperature in the past, the PCO2 in the soil, and so on. That's what we want to reconstruct, right? So it's not possible to say, okay, we can use a mathematical relationship. We can't say, hey, we know it's linear or it's exponential or it's something like that. We just know that it's complex. So the assumption of the theoretical relationship between age and distance, strictly speaking, is impossible for speleothems. However, we know a few things and we can make a few assumptions. The first thing we know, and this is a very important thing, is we know that the age model must be monotonic, right? That means that the stalagmite must become progressively older or younger with increasing distance from top, or younger with increasing distance from the base, right? We know that. And the other thing that we know is that the growth rates should neither be too high nor too low, right? They should be in the range of a few micrometers, or let's say up to 1 or a little bit more than 1 millimeter per year. So we know that the age model should be monotonic, and we know that the growth rates should be in a specific range. That's good. On the other hand, we should be aware that the age model may contain hiatuses. It may contain sections with very different growth rates, ages with very different uncertainties, age inversions and outliers. So that could happen, for instance, due to detrital contamination. So the profile could be really, really complicated, right? So this means that the age model should be described by a monotonic, but maybe complex function. So that's what we need here. Okay, a few words about the approaches that have been and are still used by the speleothem community. This is the Seisel version 2 paper, which came out in 2020. And the group from Heidelberg, Kira Rehfeld and Carla Rösch, so I think they did the majority of this work, but many other people have been involved as well. They compiled the age model types that have been used for the 691 records included in SciSL version 2. And you can see that the largest part here, 32%, did linear interpolation, right? So this is still the major method that's used to construct SpeleoThem age depth models. StalAge has been used for 13% of these records. Copra has been used for about 10%. Interestingly, 10% of the records didn't say how the age model was constructed, and many other methods. So there are Bayesian methods, polynomials, combinations of methods, and so on, right? So you can see there are a few methods which are used more often, but in general, many methods are used and have been used and are still used in the community. What's also interesting is that when they compiled all these data, they found that only for 107 of these almost 700 published records, age model uncertainties were available. And this is, of course a big problem, because it's, I mean, to estimate the uncertainty of the age model is as important as determining very precise Thorin-Uranian ages. So it's very good that they did that again. So in the SciSL version 2 database, they created new chronologies for the majority of these records using 7 different approaches. And SciSL version 2 now contains uncertainties for 512 of these records, right? So this is a large improvement from 107 records with uncertainties, with age model uncertainties. SciSL version 2 now includes uncertainties for 512 of these records. This is a complicated figure from this paper. And I don't want to go into the details here, but what you can see is they used 7 different approaches to calculate the age models for SciSL version 2. You can see this was linear interpolation, linear regression, Bchron, Bacon, Oxcal, Copra, and StalAge. And what you can see is, so black means no age model could be calculated. Gray means the age model has been dropped. And blue, or different kinds of blue, means that an age model has been calculated, but it's rated more or less successful. So in the end, you can see even the combination of all records still includes a few black lines. So it's not possible to calculate an age model for every record included in the database. But for most of them. And you can also see it's the same is the case for the individual approaches. So every approach contains black and gray bars. The message is age modeling is difficult, in particular for specific records. And there's no age model that obviously performs better or worse than the others. Okay, what I will do today now, and I said that at the beginning, I will show you 3 methods. I will introduce you to linear interpolation. I will quickly do some splines because that's identical. I will briefly show you how to use StalAge, and if we have time in the end, I will show you how to use Bchron. So if we go back to this slide, you can see we will do linear interpolation, we will do Bchron, and we will do StalAge. So you will, in the end, you will know how to apply 3 of these methods. Yeah, that's at least something. So and I think if you know how to use these methods, it should be relatively easy then for you, for example, to apply Bacon as well, because that's also written in R, and it should be possible with the basic knowledge to run Bacon as well. Okay, what I will do not today is I don't want to discuss how to fit or construct challenging age models, right? This would be a lecture of its own. I said that there may be very complex cases with hiatuses, outliers, age inversions, or combinations of all these things, and then it's impossible just to fit an age model using one of these standard algorithms. And that's beyond this lecture, right? So I just want to show you how to apply that, to do the basic coding, but I don't want to go into the details how to do that for individual records. I also don't want to discuss the advantages or disadvantages of the individual methods. I mean, we can do that in the end if there's enough time, but that's also not the goal of this lecture. And what I also won't do is suggest a most appropriate approach or algorithm, because in my opinion there is none. Right? You won't find an algorithm which performs better, or let's say better in most cases than the others. They all have their advantages and disadvantages, and some of them may work very well for some samples and not for others, and the other way around, right? So yeah, so that's the goal of this workshop, and that's what I won't do today. But of course, I'm open to answer questions in the end. Okay, are there any questions so far? Okay, good. So we can almost start with the practical part of the lecture. Just to say a few words, what is R? R is a language and an environment for statistical computing and graphics. It provides a variety of statistical and graphical techniques. This includes linear and nonlinear modeling, statistical tests, time series analysis, and so on. And that's the good thing. It's available as a free software for Unix, Windows, and Mac computers. So whatever system you're using, you can use R for free. It provides a well-developed, simple, of course, simple is relative, but effective programming language, which includes conditionals, loops, user-defined recursive functions, input and output facilities. It's a standard programming language, which is, and you can solve almost all problems with R. Why do I use R? The most important thing is that it's open source. We used to do a lot of things with MATLAB in the past, but the problem always was that when people left university, they didn't have the license for MATLAB, and then we thought, okay, R is open source, and it's much better for just for the availability, and everybody can use it for free. The other thing is new functions are produced by users all over the world, right? So it's always up to date. It provides countless applications. It's growing all the time. So in the end, it's really, really powerful. It also has a relatively good online support. So even if you're a beginner, it's possible to ask questions in online forums, and you usually you will get a reply. Disadvantages, and I put that into quotation marks because I think it's not a real disadvantage, but it may appear as a disadvantage for less experienced users. It has no graphical user interface, right? So you can't click on any symbols like you may be used from Excel or other plotting software or statistical software. It doesn't provide interdynamic graphics, so it's not possible, for instance, to rescale a plot just by clicking on the axis. And this is not important for this course, but the code is not compiled. So if your code is a bit inefficient, R may be slow. So that may be the case, but it strongly depends on how you wrote the code. Okay. Everything I will do today, I will do for an example data set, and that's stalagmite BU4 from Bunker Cave. For those of you who don't know this record, this is a cave here in Western Germany. This is stalagmite BU4. The record has been published in 2012 in Climate of the Past by Jens Vollmeister and many other people. And you can see here, this is the age model of stalagmite PU4. So here's age, this is distance from top or depth, and you can see that the age model is relatively well behaved. So we have a few ages, the relationship is not linear, but it's relatively linear. It's not very complicated. So we don't have hiatuses, we don't have large changes in growth rate. It changes a little bit. So here it's slower and it gets faster here. And then we know that it grew until modern day. So we had another change in growth rate here, but this is a relatively simple growth model, which is good for the purpose of this workshop. Okay, so yeah, now I'm gonna switch to R. Yes, can you see the R window now? Okay, so what you see here, if you haven't used R before, what you see here, and maybe I can go back to the PowerPoint, you see two windows here. One is the console window. This is the upper window here, and the lower window is the script window. So here in the upper window, this is actually where all the calculations are performed. So if we type in something here in the console window, let's say 4 + 4, you can see it does the calculation. So 4 + 4 is 8. We could also do 2 × 16 or something like that, or square root of 13, right? This is like a pocket calculator. So here in the console window, the calculations are done. And here in the script window, you can write the code. You can save the code, you can reload the code again, and so on. So here is where you...
Dennis?
Yes?
Sorry for interrupting. Could you please enlarge a little bit your the letters or the display of...
Is it too small?
It's a little bit small.
We can try.
Maybe just a little bit, yeah.
Yeah, I did that before. Let me see. So that's like this.
Yes, that's much better. Thank you very much.
So maybe I have to reload the code. Yes. Okay. Better? Good. Okay, so yes, so here above in the console window, the calculations are performed, and down here is the code, right? So if you want to try to do all the calculations by yourself, you can now start R, then you will only see the console window, and then you can say load script, and then you can just load the script that has been provided by the organizing committee beforehand. So that's what I just did. So this is the script workshop S4. So you can just load that, and then you see the same script that I have here on my screen. Maybe we should just wait a minute or so for those of you who want to try that. Okay, and when you have that, then the other thing that you have to do to do the calculations by yourself is you have to set the working directory. So you can see here, everything that's behind a hashtag is just a comment. So that's ignored when we do, that's ignored by the system, right? So everything after a hashtag is just a comment. So you can see here, this is the code for setting the working directory. And you can see, so this means set working directory, and you can see this is the folder with the data on my computer. And if you copied, or if you have the data in that has been provided beforehand in a folder on your own computer, you can just use now this folder here in this line. I will show you that quickly. So here you can see the folder in my Explorer window. You can just click here into the line, copy the line, and then you can just paste it here, and then you can just include it in this function here. There's one thing you see, if you copy and paste the folder or the directory from the Explorer, the slashes are in the wrong direction. So here in the R code, we need normal slashes, and if you copy and paste from the Explorer window, you have backslashes. So if you do that, you need to replace all the backslashes by conventional slashes, but then you should be able to run the code by yourself on your own computer. Maybe we wait another 30 seconds or so. Okay, good. So, and now if we have the code here and we have the console window up here, we need to run a command line. We need to transfer the line from the lower window to the upper window. And you can do that in several ways. You can just mark it and then use this window here. So this is in German, but it means run the line, or run the highlighted section. You can see if I push that button, the text from down here is transferred to the console window up here, and then the command which has been stored here is it's run up here. So now we have done that what's written here, right? So we have defined the directory where our data are. There are different methods to do that. The other way is pushing Control R. That's what I do. So when you see things like that, that's when I'm pressing Control R on my computer. But you can also use this window here, or this button here. Okay, so what I've done now is I told R that the working directory is this directory on my computer. And you see, this is the directory where I have all the data that I have provided or prepared for this workshop. What we have here are also the data needed for the age modeling. So in the next step, now we told R where the data are, and now we need to import the data into R, and we can do that. So you see, there's also a comment here, data import as a data frame. We can have a look at the data. So there are two text files in this folder. One is ages BU4. You can open that quickly, and you see that it contains 3 columns. One is depth, This is the distance from top. One is age. These are the ages, and one is error. These are the age errors. So these are the thorium uranium data. And then we have another text file, which is proxies BU4. And there you can see we have again 3 columns. One is distance from top. You see these are much more data. And one is delta 13C and one is delta 18O. Right? So we have 2 files. One is with one file with the age data and one file with the proxy data. And in the next step, we read these 2 files into R, right? And we can do that with a command that's called read table. So we can read a table using this function. You can see, okay, the file is ages BU4, and we tell R that the file or the data have a header. You can have a look again at the data. So the data have a header, you know, depth, age, and error. This is the header of these data. So let's do that. We run these 2 lines. You see, I pushed Control R, and now I have the 2 command lines up here. And now I read in these 2 tables, and I assigned the tables to the two variables. One is called age data, and the other is called proxy data, right? So you see, this is the table, and by using this arrow here, I can assign the data to a variable. And if I type in age data now, you see now the table has been imported into R, and it's available under this variable name, right? Age data is now our table with the age data. And we can do the same for the proxy data. So now we have the table with the proxy data available as proxy data. Okay, another thing that you need to know is how to assess individual columns of such a data table. And you can do that using the dollar symbol. So if we look again at the age data, you see this is the table. We have 3 columns, depth, age, and error. And if I now write age data dollar depth, this means that this is the data in the column depth, right? So if I highlight this, you see these are the depth data now, which are behind this variable name. I can do the same for age, and I can do the same for proxy data dollar delta 13C, for example, right? So these are the delta 13C data. Okay, so now we have actually the most complicated thing has been done. So now I think, because now we have the data available, and now we can do whatever we want with these data. And the first thing would be to plot the data, and this is also a relatively simple command. And the command is plot, and we just need to say which data we want to have on the x-axis and which data we want to have on the y-axis. And then you can see if we write plot, then x is age data depth, and y is age data age. Then you can see we create a little plot, and there we have the age data on the y-axis, and we have the depth data on the x-axis, right? And this is actually the age model that these are the ages that we've seen before from the figure from Vollmeister et al. And we can see the stalagmite grew between 8,000 years and today, and it, as I said before, it is relatively well behaved. So no large hiatuses and so on. It would be good to include some error bars. Unfortunately, that's not possible with the base R version. So we have to install a package or you have to install a package. I have done that before, but you can do that with this command line. So you just run this command line, then it tells you to identify a mirror. You can choose whatever you want, ideally something in your country. So I'm choosing Germany. And then it installs this package hmisc, which is used to plot error bars. And in this package, there is a function included which is called error bar, which allows to plot error bars. And to use this this package hmisc that we've just downloaded, we have to run this line here, library package hmisc. And then you can see, okay, now it loads this package and says, okay, everything's available now. So now we can use this function error bar. And error bar is actually relatively similar as to plot. You can see it also requires some data on the x-axis. It requires some data on the y-axis, and it also requires upper limits for the error bars and lower limits for the error bars, and that's just the age data plus the error and the age data minus the error. Maybe we can look at the data again. All right, so these are the ages, and you see y plus is the age data plus the corresponding error, and y minus is the age data minus the corresponding error. And we can do that and look at the plot again, and now you see, okay, we have okay, and if you say hey, I need I would like to have a nicer plot, then you can also add some labels. This can be done with xlab and ylab. We can quickly do that, and then you can see, okay, now we have distance from top in millimeters and we have age in kiloyears. Okay, so now we have made, we have imported the data and we have made a plot. We looked at our data, and now we can start with the age modeling. And the first thing I would like to show you is linear interpolation of the age data. And as you've seen before, maybe we can go back. This is still the most often used method for speleothems. So 32% of the records included in StalAge version 2, for 32% of these records, the age model has been originally created by linear interpolation. And the good thing with R is this can be done by one command line, right? And the corresponding function is Approx. That stands for approximate. And you just need to tell which data you want to interpolate linearly. So you say, okay, the X data are my depth data, as we have it here in the plot. The Y data are the age data, as we have it here in the plot. And then we run this approx function, and I assign the result of this function to a variable called age model linear or age mod linear. We will do that, and then we can look at this variable, and you see, okay, we get X values and we get Y values, and this is actually the linear interpolation. So these are the X values and the Y values of the interpolated record. We can also look at this age model. We just add the age model to the plot. This can be done using the lines command. So we can say lines, and then we say, okay, we want to have these interpolated X data. So you can see this is age model linear $X. These are the X values. The age model linear $Y. These are the Y values. And we can just add this age model to the plot using this lines function. And we can say, okay, we want to see that in red color. And then you can see, okay, now we have our linear interpolation age model. And that was relatively fast, actually. So if you want to do that with Excel, it definitely takes longer. Okay, but now we would like to have our linear interpolation age model at the depths of our proxy data, right? So we've seen that before. So we've measured the proxy data at very high resolution, and we have the age data at relatively low resolution. And we want to know the age of every single proxy analysis. So if we did that with 200 micron resolution, we know we need the age every 200 micrometers. That's what we want to have. And we can tell this Approx function where we want to have the linear interpolation. Because what we have is we know the distance from top of the proxy analysis, right? So this is, if you remember that proxy data contains our proxy data, and proxy data $DFT contains the distance from top of the proxy data. So we can look at this again. So here you see these are the distances where we measured our proxy data: 0 millimeters, 0.2 millimeters, 0.4 millimeters, 0.6 millimeters, and so on. And then we can use this, these data, the proxy data $distance from top, and we can tell Approx that we need to calculate the ages exactly at these depths. And we can just do that by using xout is this data. So we just add this to the command we used before. Do it again. Oops. And if we look at the result again, you see that we have many more data points here, because now we have the Y values and the X values at the very high resolution of our proxy analysis. So the X values are the depths where we measured our proxy data, and the Y values are the linearly interpolated values between the ages at the distances where we measured the proxy data. Okay, we can plot that, but it looks exactly the same. We don't see that there is a higher resolution here, yeah. So now we did the calculations as we need them. What you see here is at the end of the age model. So these are the lower end of the age model. We have several NAs. NA means not available, and that means that the age model has not been calculated for the corresponding depths. And the reason for that is that Approx does not perform extrapolation. So it just performs interpolation. It calculates the age model between the data points, but if you have a few more proxy measurements beyond your latest, your most, or your highest, your oldest sample, then it doesn't perform extrapolation. There is a way to do some kind of extrapolation. You can do that by adding rule is 2 here. You can look at this. I quickly plot this, and then you see, okay, it does some kind of extrapolation, but it just uses the latest value here. So it doesn't do something like that. It just uses the same age as the oldest age for the record, so to say. And that's usually not what we want for speleothems. The good thing is, in this package that we've just downloaded, HMISC, there's also a function included which is called Approx xtrap, which performs linear interpolation with extrapolation. And you can use it just as the conventional Approx function. So the code is absolutely identical. You just use Approx xtrap. And I assign the result again to age model linear, and then we can add that again to the plot, this time using a different color, and then you can see this time it did another kind of extrapolation. So it just used the growth rate of the oldest section and extrapolated, yeah, as we would do it without additional knowledge, actually. Okay, so now we have a linear interpolation age model for our record, and we even have some extrapolated data. So now we have an age for every single proxy value that we measured. And the final step now would be to plot our proxy data against age. So first we plot the proxy data against depth, just to show that again. With this command line here, x11, you can open a new plotting window or a new graphics device. So you can see the old plot is still here. And now we've opened a new graphics device, and the new plot will now be made in this new device. And then we just say, okay, plot the data. Now I first want to plot the proxy data against depth. So I use proxy data $DFT for the X values and proxy data $delta13C for the Y values. And then we see our proxy record, this time with points. If we want to see a line plot, we can just say, okay, type is L, and then it performs a line plot. So now we have the proxy record against depth. And now we have everything available, actually. So we have the proxy data against depth, we have the age data against depth, and we have our age model. So if we go back to this slide here, so we have this, we have a function between the individual ages, and then we can make a plot like that. And that's relatively simple now, because what we have now is we just need to combine the results of the previous of what we've done so far. And now we plot on the x-axis, we plot the age data from our linear age model, and on the y-axis we plot the proxy data. And I do that in a new window, and then you can see it looks exactly or almost the same as the data against depth, but now you can see now it's against age. So now we have the last 8,000 years here, and we have our proxy data against age. Okay, so now, yeah, we've performed linear interpolation for our record. And the final thing would be, if you don't want to do the plot in R, and I guess most of you don't want to do that, you probably want to export the data, and then you can do it like that. I think that's not included in the code that has been uploaded before, because I added this line just 5 minutes prior to the lecture. So, but we can send around the updated code. You can use this command line here, which is write table. That's very similar to read table that we've used to import the data for data table. And then we just want to export the age model. Age model linear is our age model data, and then I can say, okay, the file name should be results point text or something like that. Let's do that. And then you can see in your folder there is a file results.txt, and if you open that, this contains the age model, right? So here you have the distances, 0.2, 0.4, 0.6, 0.8, 1, and so on. And here you have the corresponding ages. Okay, and that was the linear interpolation age model. Are there any questions? Okay. Then I go on. The second thing I want to show to you is fitting splines. This is, I wouldn't suggest to use.
Sorry, Dennis, we do have a question in chat.
Okay.
And the question is, does this code run on Python platform as well?
I'm sure no, this code, the identical code doesn't, but of course you could run a very similar code on Python. That should be possible, but the syntax is a bit different. Fortunately, I can't see the chat because I only have the Zoom window with the pictures of you, but I can't see the rest of the Zoom window.
You should be able to open it at the bottom. You should have like a chat icon.
Yeah, I have something, but.
And then it should open, maybe if you're using two screens, on the other screen.
Chat. Okay, I see the chat. That's good. Okay, so the answer is no, it doesn't, unfortunately. But you could, I think you could easily, if you're familiar with Python, it should be no problem to adapt it to Python. That should be possible. Okay, so I go on with fitting splines, not because I want you to use splines for fitting age models with SpeliaThems, but just to show you that it's really that it's what you can do with R, because the code is almost identical. You just we just replace the Approx function by Splines. So I will do that relatively quickly, and you can play around later with the code. That should be, I think that's the best solution. Okay, so fitting splines using the spline function. So first, we again plot the age data. That's what we've done before. So we have again our age model. And when we did the linear interpolation, we used a function called Approx. And we said, okay, use the for X, we use the depth data of the age data, and for Y, we use the age. And we said, okay, do the interpolation at the proxy depths. And you see the command is absolutely identical, but now it's spline and not Approx. And I assign the result to age model spline, right? So we do that. We can add again the age model to the plot, and then you can see the difference to the linear interpolation age model. The spline is just a bit smoother. So the linear interpolation, of course, changes exactly at the ages, and the spline is a bit smoother. On the other hand, the spline does a few things that may not be supported by the age data. So you see here that it does some swings which may be not real. Okay, so you can see that there are different methods. So this was the method FMM. You can also say, hey, use another method. There's, for example, method natural. We can have a quick look how that looks like. And you see it's relatively similar, but it does a different kind of extrapolation. So the FMM spline did something like that, and the natural spline does something like that. So there are differences, but they are minor, I would say. We can also compare the two splines. So we look at, we now plot the age model, the proxy data against these two spline age models. First we look at the proxy data against the age model with the FMM spline. And then I just add the age model with the other spline, with the natural spline, and then you can see, okay, the differences are really minor. So the major difference is here. So here they're absolutely identical. Here there are a few differences, but the major difference is here in the part where we have the extrapolation, because the extrapolation is different for the two kinds of splines. We can also zoom in and look at this section. So I can do that with xlim. I can scale the x-axis, and then we can see, okay, there is a difference in the extrapolation, and it's about, let's say, 300 to 400 years. So the natural spline does a stronger extrapolation here, and then the oldest part of the record is 8.4. And if we use the other spline, the oldest part of the record is 8.1. Funnily, there is a peak in this range here, and we always thought that this peak might be the 8.2 event. And you see, whatever age model you use, you either have an 8.2 event or you don't have an 8.2 event. In the end, it turned out that we don't really have a strong 8.2 event, but you can see it may be crucial. The age modeling, in particular in the parts where you have to extrapolate, may be crucial for questions like that. Okay, and if you really want to see the difference between two age models, you can of course always calculate the difference between the ages, and I do that here. So we have I do that here for the linear age model and the natural spline. So I just calculate the difference between the age model linear minus the age model spline. And I assign this to a variable called diff for difference. So this calculates the difference between the two age models, and then we can plot this again against age, for instance, and then you can see, okay, this is now the difference between the linear age model and the spline age model. So maybe we look at this is the spline age model, and this is the linear age model. Right, and this is the difference between the two, and we see the difference is never larger than 150 years or something like that. Interestingly, the largest difference is here in the middle, somewhere in the middle, and not in the parts where extrapolation takes place. But that's what I meant at the beginning. So if you have a well-behaved stalagmite and a well-behaved age model with relatively simple relationship, most age models will produce very, very similar results. It becomes interesting and also more difficult if you have a challenging age model with hiatuses, inversions, and things like that. Okay. Are there any questions? Okay, so I have another 30 minutes, so I'm not too bad in time, that's good. And what I want to show you now is StalAge. For those of you who don't know StalAge, you can see that it has been used for about 13% of the records contained in, or that have been included in SciSol version 2. StalAge has been developed by, where is it here? By Dirk Hoffmann and me in 2011. And there's actually, and I think that's one of the advantages of StalAge, it's written in R, but you don't have to know R to apply it. So there are detailed step-by-step instructions available with the code. So how to install the code, how to prepare the data. You have to type into the console window and how to export the data. So even if you don't know R at all, you can run StalAge and calculate the age model. And it has worked for many, many people. Unfortunately, for some samples, it may be possible that StalAge doesn't work with the most recent versions of R. I have experienced that. We will see in a minute that with the example that I'm using now in this workshop, it's no problem at all. But it may be possible if you have a complex record that it doesn't work with R 4 point something. If this is the case, you can either go to our homepage here and download the original files. So there is the old R version that we used to write StalAge, and then you can follow the instructions provided on the homepage, or you send me an email. That's the other option, and then I can try to run StalAge with your age data. And usually it's not too much work for me, and I'm able to provide the data relatively quickly. Okay, so now let's have a look how StalAge works. The first thing that we have to do is we have to load the StalAge code. The StalAge code is also available in our folder, and I think it has also been sent around beforehand. So this is the StalAge code. You can open that. You see, this is the code performing the age modeling. And to load the code into R, it has to be in our working directory. And then we can just type source file is StalAge.r, and then the code is available. And now we have to install a few packages. I have done that before, but we can do it again now. Should be relatively fast. Yeah. Packages. These are required for running StalAge. We have to make the 2 packages available that we've just installed. And then we can use exactly the command lines provided manual. So if you go to the paper, read the original paper, it says, okay, first type in this line, then type in this line, and so on. And instead of typing them into the console window, we now do it like that. So what we do is we import the age data. Then we attach the age data. This is actually not necessary. That's what we've done so far using the $ symbol, but for StalAge, it has been done like that. Don't worry about that. We do the same with the proxy data. So now these data are available. So you can see the age data are available with this variable, and the proxy data are available here with this variable. So that's exactly the same that we've done before with the linear interpolation. And that's what I consider as an advantage of StalAge. You don't have many parameters to play with. Actually, you don't have any parameters to play with. So you just have 3 command lines, and the code will always produce the same result, whoever runs it on whatever platform. So the first command line is scanning for major outliers. We can do that. And you see it opens a new window, and the data look exactly the same. So it first makes a plot with the original age data, and then it makes another plot for the age data screen for major outliers. But of course, we don't have any major outliers here. So yeah, no outliers have been identified, and the age data are exactly the same as before. In the second step, StalAge scans for minor outliers. This is done with a function called scanFine. We can quickly look at that, and you can see that was really fast. What it does is it enlarges the error bar of the topmost age. So this is something we could, of course, discuss about, but what we did when we when we created StalAge was we said, okay, if there's a large change in growth rate, for example, here we have the growth rate like that, and then the growth rate changes for the last age at the top, right? And we said, okay, if there's a large change in growth rate, which is only supported by a single age, we say, okay, this is maybe too optimistic to say, okay, all these ages are correct, and just based on this single age, we model a large change in growth rate. So what we consider this age here as a minor, what we call a minor outlier, and then the error bar of this age is increased. Actually, we know that many people don't like this behavior because it tends to do that, particularly at the topmost, at the ages at the top and the bottom, because it often happens that at one age at the top or the bottom suggests a different growth rate, and then it does exactly that. So there's a way around that, and we have done that before in publications, but actually it's designed like that, and now we do it we treat it like that, and you will see that the effect is actually not too large. Okay, so we have identified a minor outlier here, and that resulted in a larger error bar here at the top. But apart from that, nothing has changed. And now we do we have the third command, which is the actual age modeling. So this is this line here. And now it does the age modeling. So you can see what it does. It fits ensembles of straight lines through the age data, and then it uses all these linear fits, so to say. So all these linear fits created here to calculate a mean age model from these fits. And then you get two plots in the end. You get the final age model with the screened errors, and you get the final age model with the original errors. So as we just discussed, the only age that has been, or the only error that has been enlarged by the screening is the age error here at the topmost age. And you see that with the enlarged error, the age model and also the confidence limits goes well through these bars. And if we look at the age model with the original errors, you see that the age model doesn't go through the original age, the topmost age. And that's what I just said, because we said, okay, we don't want to model this large change in growth rates just based on that single age. But you can see that it also assigns a very large error to this section here. So it models, it doesn't force the age model through this age, but it assigns a relatively large error for this section. So yeah, this is, as I said, something we could discuss about, and I know that many people don't like that behavior, but within error, the topmost age is also included in the age model, I would say. Okay, and now the age modeling is done. We can look at the results. So the age model has been assigned to a variable called fit, and now we can look at the table that is that's included in fit, and you can see we have here the x values. So these are our depths where we calculated the age model. We have the y values. These are the ages of the age model. And then we have y plus and y minus. These are the confidence limits, the 95% confidence limits. Yeah, and now you have everything again, and you could export these data and plot it in another software. But what I want to do now is I want to compare with the other age models. So first of all, we just look at these age models. So I make a quick plot, and here you can see, so this is the linear interpolation age model that we did first, and then we have here the spline age model, the natural spline, and this is StalAge down here. And as expected, they are all very similar for the large majority of the record. The only difference is, of course, here the topmost section, because StalAge didn't force the age model through this age here at the top. And maybe what I should say is this is not a uranium series age. This is just the date when the speleothem was sampled in the cave, because we know that it was active. We also had bomb C14 at the top, so we know that there was recent growth, but this is not a uranium series age. So we know that it was recent, but we don't know what happened in between. Yeah, okay, so now we have 3 age models. We have linear interpolation, we have StalAge, and we have this spline age model. And now we can again calculate the difference. So what I do is I calculate the difference between the linear age model and the StalAge age model. So this is this here. It's again assigned to a variable called diff. And then we can plot the difference and that there is not a large difference between the linear age model and the StalAge age model, right? It's 300 years here in this section. And if you remember, we also had a difference between the linear age model and the spline age model in this section here. And then, of course, we have this difference here of up to 400 years at the top, which is due to the behavior at the outer limits of the speleothem. Okay. But, and that's important, if we now add the uncertainty of the StalAge age model to this plot, so this just adds the lines, the error, the confidence limits of the StalAge model to this difference plot, and then you can see that even if the StalAge age model doesn't force the record through the topmost age, within the uncertainties, they're almost identical, right? So the linear age model and StalAge, they differ by, let's say, 400 years, but the uncertainty of StalAge is about 400 years in this section. So within error, they're almost the same.
Dennis, there's a question from Paul.
Ah, okay. Can you project the uncertainty from the age model onto the proxies? No, you can't. Well, you could actually. That would be possible. You could use the StalAge output for a calculation, as they've done for Cobra, but it's not available yet. So it's not included in the software. Okay, I have 15 minutes left, so I will quickly show you how to use Bchron. And that's particularly interesting because Bchron is a Bayesian algorithm, and it's available as an R package. Oh, there's another question, but I only see the beginning of the question.
It says that what do you do if you have a hiatus in your data? How do you take care of it?
Okay. I always suggest, if there is an obvious hiatus, I would fit the individual sections one after the other. I mean, all these algorithms have problems with hiatuses. StalAge, I think StalAge is not bad in identifying hiatuses, but if you know that there's a hiatus in your data, I would always suggest to separate the data at the hiatus and then fit 2 age models. That's always better.
Yeah, Maciej, go ahead.
Yeah, thanks for that. Probably it was me asking this question, but I couldn't write it all the way. Thank you actually for this answer. Also, like if sometimes you just don't have so many dates. So like in between, if you have two hiatuses and in between you only have two dates, would it be like, what's your opinion? Like, can I actually use StalAge for one part of the stalagmite and then use the linear for the other part when I only have two dates, and then StalAge for the third part of the stalagmite? Just ask, like, what would be the best thing?
Yeah, actually, you would have to do something like that, because StalAge always needs 3 ages. So if you have a section with only 2 ages, StalAge will fail, because that's one of our basic assumptions, that we always need 3 ages to construct an age model. And actually we have done the same. If you have a very short section, let's say you have a flowstone which just grows for 200 years and then off, and then for another 200 years and so on, and then I would suggest to use any algorithm like StalAge for the longer sections with several ages, but then maybe use linear interpolation for the short sections where you only have 2 ages. That's yeah.
Thank you.
Okay. So yes, I quickly want to introduce you to Bchron. Honestly, that will be a bit more complicated than what we've done so far, simply because the algorithm has more options, and the output is also a bit more complicated. But at least you have the code, you have the video, you can watch it again, and to apply it to your data, but just replacing or just using the same command. Okay, Bchron comes as an R package, so we again have to install this package using this code that we've seen before. So it installs the packages. We have to load Bchron, the Bchron library. Okay, so my R version is not the most recent, but that's not a problem. And now Bchron is available. And the first thing is Bchron works with years rather than kilo years. So the first thing that we have to do is we have to multiply our age data by 1,000 to convert it to years. So this is simply our age data now in years, and we used to have it in kilo years. And then we do the age modeling, and you see, no, you don't see it because you see that this is a bit more complicated than the command lines that we've used so far, but it's in principle it's the same. So you need to provide ages. So these are the ages. We need to provide errors. So these are the age errors. Something that is important here is usually when you have uranium series data, we provide 2 sigma errors, but Bchron, because it has been developed for C14 dating, it expects 1 sigma errors. So you have to divide all the errors by 2 to avoid to do the simulations with too large errors that are too large, right? Positions are the depth data, so that's the same that we've used before. Cal curves is something that's usually used for C14 dating, because you could also do C14 calibration here. We don't have to do that. We assume a normal age distribution, and you can do that with this command line. So you could just use exactly the same code if you want to do the calculations by yourself. The predict positions are the proxy data depths. So that's what we've used before. That's the depths where we have our proxy data, and then we can say how many iterations we want. How many of these iterations we want to throw away. So this means we perform 5,000 iterations and we throw away the first 500. And actually I forgot what thin is, but it can't be too important. So let's do it like that. And the function for age modeling is Bchronology. So let's run this, and the result is then assigned to BU4 Bchron. And you will see that this takes a bit more time. So this is with 5,000 iterations. It takes, of course, longer if you do more iterations. And it seems that Zoom is slowing down my computer because it was faster when I tried it before. But it's almost finished.
I would like to ask you, why do you exclude first 500 iterations?
Yeah, that's Bayesian algorithms. How should I explain that? So you do a simulation of the data, and the simulation it accounts for the succession of the data. So it uses the assumption that the age model must be monotonic. And but in the first, let's say, when it starts, it just simulates the ages according to the errors. And if, let's say, if the first simulation is unusual, it could be that these first simulations are not representative of the whole data set. So it needs just some time to get, let's say, the whole, to represent the whole data set. So you need to throw away a few of these ages. I don't know if 500 is enough. So you could also perform 10,000 iterations and throw away the first 1,000 or so. That could also be an option. But I think it should be fine.
Thank you.
Okay, so now let's have a look at the results. We can do that with some summary functions. You can see that, for example, this command line gives us some quantiles. Where is it? No. It's here. So these are the quantiles of the predicted ages by depth. So you see, okay, this is depth. These are our proxy depths. And then you can see, okay, the mean age is minus 50 C14 years. So this would be the year 2000, actually. And this is the 2.5% confidence limit. This is the 97.5% confidence limit. So it says for the top that the age is somewhere between 1990 and 2017, right? And so on. So we can calculate confidence limits or quantiles for the whole profile. We could also look at outliers, because Bchron also checks for outliers. Of course, in this profile, we don't have any outliers. And you can see it calculates the outlier probability, and it's below a percent these ages. Actually, date 1, which is the date here at the top, has an outlier probability of 1.6%, right? So it's like StalAge. It says, okay, the growth rate changes here, so maybe there's something wrong here, but the probability that it's a real outlier is really, really low. Okay, and then we can plot the results, and here it's really easy. You just say plot BU4 Bchron, and then it produces, well, that hasn't happened before when I tested it in the afternoon. Well, that's interesting. Okay, so maybe I have to run it again, maybe with less simulations to save time. 2000. Let's try it like that. That's interesting. I tried it before several times, and there was no problem. Okay, let's see if it works now. That's unfortunate now. Missing ties. Okay. One more try. Okay, that's good to hear. Don't know why it doesn't work with my code now. Run completed. Okay, that's unfortunate. Did I change anything? No, don't think so. Okay, that's better if it works on your computers and it doesn't work on mine, rather than it works only than if it only works on my computer. But it's still unfortunate because I can't go on. Maybe I do. I try it once again with 5,000 iterations. Data DFT. Age is not given as whole numbers. This is and maybe the warning messages are not a problem. Let's see. Okay. Well, the question is where the age model is. Here it is. Haha. Okay, now it worked. I don't know why it didn't work before, but here you see the age model, and you see it's kind of a sophisticated plot. So here is age is now on the x-axis. Depth is on the y-axis. That's because it has been developed for sediments, so they tend to plot it like that. You can here see the distributions of the individual ages, the error distribution of the individual ages. But what you see is, what you get is, in principle, a linear interpolation age model with some confidence limits around it. Okay, so and now I have to speed up a little bit. We can look at the results, right? So the results are contained in this this variable Bchron, BU4 Bchron, and with $theta you can look at the simulated ages at the different depth. We can also look at the ages modeled at the different proxies, and you see, because we did so many simulations, these are very, very large data files. We can also look at which depth we did the simulations. So BU4 Bchron $predict positions, these are our proxy depths. And then I recalculate the ages in kilo years again for comparison with the other age models. I calculate means, medians, and so on. And now we can plot the results, and that's maybe more interesting. So we plot the ages again. And now you see, these are now the ages simulated by or calculated by Bchron. And you see they're very, very similar for most ages, but here, for example, the red age is a bit lower than the black age. Same here, the red age is a bit lower than the black age, right? So the 4,500 simulations, they resulted in a slight shift of the original age data. Matej, there's a question.
Yeah, sorry to intervene, but I have one question that's actually rather subjective, but I still want to know your answer. Let's say that you have out of 20 ages, like you've got one age that is not like right, you know, like it's reverse, or it's like really going like, you know, minus or plus.
Yeah.
What do? Like, I can actually incorporate it, and I've been using your syntaxes, and actually they're really working well. But I can actually exclude it, and everything's perfect. Or I can include it because I've done it, and everything's different. So maybe it's a bit subjective, so you can be political in the answer, but just
Yeah.
out of your experience.
Yeah, maybe we just finish the Bchron part, and then we can discuss these general things. Okay.
Yeah.
But
That's
actually that's an important question. I agree. Yeah, I don't know if I can provide a satisfying answer, but I will try. Okay, so what we see is the modeling, it changes the ages, the individual ages a little bit, you know, so that comes just from all these simulations. It calculates new age distributions, but for these ages, it doesn't have a large effect. But for example, if you had an outlier, it could have a large effect. Right, so this is the same, and now we can show the age model. So this is now the Bchron age model, and you see that it looks like linear interpolation. So it does all this Bayesian modeling, but in the end, for such a relatively simple age model, like the one of BU4, the result is almost identical to a linear interpolation age model. The advantage is, of course, it calculates these age uncertainties. That's what we've seen before in the other plot. So these are the 95% confidence limits. So that's an advantage compared with the linear interpolation age model. And now we can again compare with the other algorithms, for example, with StalAge. So this is the Bchron age model, and now I add the StalAge age model, and what you see is for most parts of the record, they are really similar. There are differences here. For example, the Bchron age model runs through this age here, while StalAge rather does something like that. So, but within error, if you compare the confidence limits of both algorithms, they always agree, right? So within error, the age models are identical. If you plot the proxy data, of course, the plots may look different. For example, here, where Bchron forces the data through this point here, and StalAge does something like that with a large error. But within error, they are always identical. And we can also look quickly at the difference again, and you see it's again, the differences are not large. So here they are 200 years, and here, and this is again the top section where StalAge does this other approach, and it's up to 400 years. Okay, and that's it. So yes, I think I stop here, and now you can either ask technical questions or general questions concerning age models. Many questions at once. Shall I just answer the questions from the chat step by step? How StalAge is effective for C14 dates of sediment core samples? Good question. So StalAge doesn't do C14 calibration. So you can't simulate, you can only simulate normally distributed ages with StalAge. So you can't simulate C14 ages. But you could include, in principle, you could include that in R, but you would have to modify the algorithm. Does that answer the question? Obviously. Okay. Would StalAge or Bchron be able to incorporate an annual laminar count I have done? If not, which modeling method would you recommend? It's not. I think for StalAge it's not possible. For Bchron, I'm not sure, but I also think that it's not possible. It's possible with Cobra, as far as I know, at least to some extent, but I never did it. I've never used it by myself, but I think with Cobra it's possible. If our sample has not grown until present day and our topmost date is at the topmost part of the sample, the have not grown till present day and our topmost date is at the topmost part of the sample. I think I don't get the question. So the sample has not grown until today, and the topmost date is at the topmost part of the sample. But then everything's okay. If you have an age for the topmost section, then you can just run the code as it is, I would say. The problem is if you have, let's say, you have your youngest age at a distance of 5 millimeters and you have another 5 millimeters of proxy data, because then you have to do an extrapolation, which is associated with more uncertainty.
Hi, actually, I asked a question regarding that. Like, let's say my topmost part of my sample, I don't have any proxy like uranium series date, but I need to extrapolate that from the younger side also. Is this possible to extrapolate to the younger side, like older side we are doing? Yeah, that's possible. Most of the algorithms would just do that automatically. Okay, and I have one more question for Bchron. You have used like normal for cal curves. Let's say if I want to use Bchron for sediment samples, can I use incal or something like that? Yeah. And then how do I do that? That's a good question. It should be, so you can use the help. So if you go to help, this is German here, but it should be help and then R functions. And then you can, it's Bchronology, I think. I think it's Bchronology. Where's the age model? Yeah, so you could look it up here. So here's the description of the Bchronology function, and there is cal curves, a vector of the values containing either incal 20, SHcal 20, marine 20, or normal. So it should be possible just to use incal 20 and then it do the calibration. Instead of like I need to just remove the normal thing and I need to put incal, or where I should. So yeah. Okay, so cal curve equal to, it will be incal 120 or whatever I want to use. Yes. Thank you. So I see no more questions in the chat. So maybe we can come back to Matej's question.
Can you repeat the question, Matej?
Matej, are you still with us?
I think he is, but the connection is very bad.
Sorry, yeah, I'm still with you. Sorry. Yeah. So yeah, it was a question which is actually rather like subjective, you know, in terms of like you actually have like about 20 dates or like 30 dates or whatever, and then you've got one date that's really out of the sketch, like out of the, you know, reversed. What do I do? Like I've tried everything, like in terms of that. So I'm actually just looking for experience. Like, so whether you actually like, if you cancel it and you don't put it in, you can actually have a really nice curve and really great age model. But at the same time, you actually like, you know, did the dates. It could have been actually a bit of contamination. So like you can actually count of that, but at the same time, it could have been like the right one. So you can put in the model and you actually get like a really wide range of the dates. Yeah. So basically I'm asking for the experience in terms of like, what have you done if you've come across this kind of a problem?
Yeah, I mean, something like that happens. For sure. The official answer would be if there is, if you don't have any reason, let's say you know that there was a problem during dating, or that you have that there's no evidence for open system behavior or contamination of the sample. So if there's no obvious reason, I wouldn't say that it's justified to just exclude it. And on the other hand, it of course depends on the size of the outlier. You know, if you have, let's say you have your speleothem, let's look, if it plots up here, I would say, hey, okay, it's 4,000 years too old. There's obviously something wrong, so you can throw it out. If it plots up here, then, and if you have overlapping error bars, then I would say leave it in, because or do it again. Try to date it again. Maybe this, if you have the time or the material and the money, and then try to date it again. So it's tough. I'm convinced that many people would just throw it out, but yeah, I mean, with
fair enough. I'm thinking the same way. So like, fair enough. The redoing it would be the best choice. So yeah, but fair enough. Just to know the other experiences, we all have the same ones.
Yeah.
Thank
but
you.
I think it happens. It happens from time to time. You know, if you do, let's say, if you have, as you said, if you have a speleothem with a record with 20 or 30 ages, it's almost normal that there's one age which plots kind of off from the stratigraphy, and you don't know why. So that's the message actually is, you know, we always tell people that speleothems are the material that's and that we can date it with the highest accuracy and precision, and I'm convinced that this is the case. If you compare it with all other archives, our greatest advantage is that we can date our material very, very precisely. So but that doesn't mean that every speleothem is perfect for dating, right? So we still have samples which have subtle open system behavior, which is, and there's no chance to identify that before you do the dating. So you cannot exclude that there are slight inversions or outliers or something like that. And I think most of us have also even seen bad samples, which are really, really difficult to date. So yeah, so we shouldn't tell that the others, because the message is not that speleothems are difficult to date. Speleothems they provide the most accurate chronologies, much better than most other archives. But still, that doesn't mean that everything's straightforward. That's maybe the answer.
Thank you. Appreciate your talk.
We have one more question in the chat.
Yeah, okay. Yeah. Do you think it would be difficult to implement variable? No, it isn't. Actually, we've already developed such a code, which is kind of hidden in a paper of one of my PhD students from 2019 or something like that. And we're working on a version that can be combined with StalAge, and of course we would then make this code available to the community. That's actually something really useful, in particular for samples with strong contamination. It's sometimes very useful to play around with the correction factors, and then you can solve things like that with reversed ages. So I hope that this will be available, let's say, in the next year or so, maybe half a year.
So if there are no more questions, I think we are moving towards the end of this meeting. Thank you very much, Denis, for this workshop. It was very interesting.
You're welcome. And I wanted to say that it's you know, I have been part of the very first summer school, and I think that started with 30 PhD students or something like that. So it's great to see so many people here. And I think Marie said you had 250 in total.
Yeah, it was about 250.
Yeah, that's amazing. That's really because that shows that it's growing the community, and that it's still important and interesting what we're doing. That's great. And thanks for you for organizing all this.
Oh, thank you. Yeah. So, yep.